Hello everyone, this is Ruiyuan Li from Chongqing University Start Lab. I'm glad to introduce our work about ELF, erasing-based lossless floating point compression. With the development of sensor devices, there is an explosion of floating point time series data in a streaming fashion. For example, the sensors in a Boeing 787 can generate up to half a terabyte of data in a flight. To reduce the bandwidth and storage cost, this data needs to be compressed before being transmitted and stored. In some scenarios, such as network transmission, data management, and scientific calculation, it requires a lossless compression because any error could lead to a disastrous consequence. Existing solutions have several drawbacks. The general methods, such as gzip and ZSTD, only work in a batched mode. They also face the problem of inefficiency. Loss floating point compression methods would lose some information, so they cannot be applied to those critical scenarios. Existing lossless float point compression methods, such as Gorilla and Chip, still ends with unsatisfactory effects. These lossless methods are based on an XORing operation. In the process of compilation, they first perform an XORing operation on two consecutive values, and then encode the XORed value. In the process of decompression, they first decode the XORed value and then perform another XORing operation. Since two consecutive values in a time series do not vary much, the number of leading zeros in the XORed value tends to be large. However, how about the number of trailing zeros? In fact, most of the XORed values contain very few trailing zeros. If you only consider the previous one value, just like Gorilla and Chip did, 95% XORed values contain less than 5 trailing zeros. Even if we consider previous 128 values, just like Chimp 128 did, there are still 60% XORed values containing less than 5 trailing zeros. Few trailing zeros lead to an unsatisfactory compilation ratio. As a consequence, increasing trailing zeros plays a fundamental role in enhancing the compilation performance. The main idea of ELF is to erase the last few bits of each value, that is, setting them to zeros. So the XORed value can contain many trailing zeros. In this example, we erase the last 44 bits of 3.17. We can obtain an XORed value with as many as 44 trailing zeros. During decompression, we can restore the original value with a leave-out operation. For example, since we know the difference between the original value and the erased one is less than 0.01, we can safely infer the original value as 3.17 by leaving out the digits after 6 and then plus 0.01. Yes, this is the ELF magic. It can not only greatly increase the number of trailing zeros, but also magically join a broken mirror together. ELF works in a streaming fashion, whose framework is shown in this figure. There are still 3 challenges to be addressed. First, how to efficiently determine the erased bits. Second, how to compactly encode the erased data. Third, how to losslessly restore the original data. To address the first challenge, we review two definitions here. The first one is decimal place count, which presents the precision of a decimal value. For example, the decimal place count of 3.17 is 2. We denote the decimal place count as alpha. The second definition is Mantissa prefix number. A Mantissa prefix number v prime of v is obtained by erasing the bits after Mn in v. This picture gives three Mantissa prefix numbers of 3.17. As a result, the problem of determining erased bits takes into finding a Mantissa prefix number v prime, which contains trailing zeros as many as possible. At the same time, the difference between v prime and v should be less than 10 to the power of negative alpha. Thus, we can restore v without any loss. The basic method is to enumerate all of the Mantissa prefix numbers of v, and then find the best one. However, it may execute up to 52 times, which is rather time-consuming. Alf proves that if we erase the bits according to this equation, we can directly obtain the best Mantissa prefix number, which only takes 01. For the second challenge, our erasing strategy is based on Gorilla but with 3 optimizations. In Gorilla, it takes 5 bits to record the number of leading zeros. However, we find that the number of leading zeros is severely unbalanced, so we approximate the number of leading zeros with only 3 bits. For example, if the number of leading zeros is 13, we regard it as 12. Thanks to the erasing technique, the XOR value tends to have both many leading zeros and trailing zeros. That is, the number of sent bits is usually no more than 16. So, using 6 bits to record the number of sent bits is not quite effective. To this end, if the number of sent bits is no more than 16, we use only 4 bits. Otherwise, we still use 6 bits. Although we need 1 extra bit to distinguish these two cases, it is supposed to take up less than 6 bits on average. We also find that the case of identical consecutive values is infrequent, but this case takes only 1 flag bit. Other frequent cases take 2 or 3 flag bits. To reduce the overall flag bits, we reassign the flag codes, so each case takes only 2 bits. Recall that to restore the original data, Alf performs a leave-out operation on the XOR value, and then adds up 10 to the power of negative alpha. But how to obtain alpha? One basic method is storing alpha with 9 bits. Since the maximum possible value of alpha is 324, alpha stores beta instead of alpha with only 4 bits, as alpha can be calculated by beta. Beta is the decimal significant count. For example, the decimal significant count of 3.17 is 3. Alf proves that the number of erased bits depends merely on beta. If beta is greater than or equal to 16, the number of erased bits is less than 4 as a result. To ensure a positive gain, we only store beta if it is less than 16. We can calculate alpha by beta and the start decimal significant position as p according to this equation, where SP means the first position of digit that is not equal to 0. Since beta will not be 0, we utilize 0 to record the case where V has a format of 10 to the power of negative I. We verified the performance of alpha with 12 baselines based on 22 datasets. The metrics include compilation ratio, compilation time, and decompilation time. For roll-off 3 metrics, the smaller, the better. The results show that, compared with the best streaming competitors, Stream 1 to 8, alpha enjoys a relative 12.4% improvement of compilation ratio, while maintaining a similar efficiency. Compared with the best general-purpose competitor XZ, alpha still has a competitive compilation ratio, but it takes much less compilation time. We also investigate the performance on the data with different decimal significant count beta. Compared with Stream 1 to 8 and SNAPY, if beta is less than 13, alpha always performs the best in terms of compilation ratio. The erasing technique proposed by this paper can also greatly enhance Gorilla and Chimp. However, the erased enhanced Gorilla and Chimp still perform worse than alpha, which verifies the effectiveness of the proposed encoding strategy. We released our source codes and datasets to the public. Our paper will be considered as the most reproducible paper award in VLDB 2023 conference. Recently, we proposed several upgraded versions of alpha, including alpha plus, alpha star, and self star. These methods enhance the performance further. In particular, compared with alpha, self star achieves a relative compilation ratio improvement of up to 20.8% while maintaining similar efficiency. Alpha star even outperforms XZ by up to 13.3% in terms of compilation ratio, but it takes only about 4.8% compilation time. Interested readers can refer to the papers uploaded to arXiv. If you have any question, please feel free to contact me. Thank you.